So let's say we've got that parameterized line. You can write it like this, or if you just kind of remind you write it like this, or if you want, you can write it as like R of t as a vector is. I'm gonna write it like, I mean, really, it's the same thing. 5 plus 3t, 2t, 4 minus t. So you've got your parameterized line. And a point. Not on the line. So I don't know. 6, 2, 1. We want to find the equation of the line that includes that line at that point. Or sorry, the equation of the plane that includes that line at that point. Okay, great. So here's kind of the idea of what's happening. There is some plane that includes that line at that point. For sure, there has to be, right? So here's the line here. And let's call this point P. Here's the point here. So to find the equation of a plane, you essentially need what I think of kind of is really needing is for a plane, we need both a point, which we have certainly, and we need a normal vector.
What is a normal vector?
Perpendicular vector to the plane, right? So we need the vector that is perpendicular to the plane that we don't know the equation of yet. It's all right. That's always what we really, when you really get down to it, like that's what you really need to find the equation of a plane. Is you need some point in the plane, and you need some vector that is not some, the vector that is perpendicular to, right? Because there's really only, I mean, get technically there's two, but there's really just one. So the way you find a perpendicular vector is you need two vectors in the plane, and then you can take their cross product to find the vector that's perpendicular. Well, we've already got one vector. One of the vectors in the plane is just the vector that's the direction of the line. So that's going to be 3, 2, -1. That's from the line. The other vector we're going to make up by taking any point on the line and drawing or getting the vector from the point on the line to the point that's not on the line. Because I should say, to get a perpendicular vector, you need two vectors that aren't in the same direction, right? To be able to cross product and something sticking out. So we're going to just grab some point on the line. I'm going to grab that point by letting t equal 0. And if t equals 0, I get the point 5, 0, 4. And then I'm going to draw that vector. I mean, you don't really have to draw any of this picture. I'm just drawing it to kind of show you what's happening. So we call that point S. Then the vector SP is, well, it's ending at P, which is 6, 2, 1. And starting at S, which is 5, 0, 4. So 6 minus 5 is 1. 2 minus 0 is 2. And 1 minus 4 is -3. And then we're going to take the cross product of these two vectors to get our normal vector. So let's see. So V cross SP IJK. Got 3, 2, -1. We've got 1, 2, -3. I feel like these are very similar looking, even though I just made them up. Such is life. So then we're going to get I times the determinant of 2 times 2, -1, 2, -3, minus J times the determinant of 3, -1, 1, -3, plus K times the determinant of 3, 2, 1, 2. That's going to end up being, let's see, -6 minus -2 is -4i. And let's see, -9 minus -1 is -8. So, but it's positive, so plus 8j. And then 6 minus 2 is 4.
Is it subtraction when you're doing the determinants? So it's the diagonal.
Well, it's always the product of this minus the product of this. And then you could either use this vector or you could use a lesser multiple of it. So for example, if instead of using this, you could say that's n, or if you prefer, we could say the normal vector is like maybe -I plus 2j plus k. they're parallel to each other, so it doesn't matter if we use the one that's larger or the one that's small. Right, exactly. Totally fine. So then if I want to find the equation of my plane, I'm kind of running out of room for here. Well, now I've got the normal vector and I've got my point, and you can pick any point you've already used. Then the equation of the plane, you're just going to take the coefficients of I, J, and K and make those the coefficients of X, Y, and Z. For our plane is going to be negative X plus 2Y plus 1Z equal to some constant. And then to find that constant, we plug in any of the points in the plane. If I plug in 6, 2, 1, I get negative 6 plus 4 plus 1 equals D. So that's going to be negative 1. So finally, the equation of our plane is going to be negative X plus 2Y plus Z equals negative 1. That's not the only way of expressing it, right? You totally could have just as well written X minus 2Y minus Z equals positive 1, but either way is fine. This should be the plane that, and so if you wanted to check, you can check that this other point actually also satisfies the equation. If I plug in 5, 0, 4, yep, negative 5 plus 0 plus 4 certainly does equal negative 1. So this point that's on the line and this point that's on the line are both in the plane. So kind of to sum up here, whenever you're trying to find the equation of a plane, you typically need to get a normal vector. And to get a normal vector, we typically do that by taking two vectors that are in the plane and taking their cross product. Questions, comments? Cool. You also mentioned that there was a question similar about finding like the equation of a line based on something.
It was like given a line that is perpendicular to the plane,
Mhm.
with a point something,
Mhm.
find the equation of the line. Something like that.
Hmm.
I was like, if it's perpendicular to the plane, then does that mean?
Sure. Okay. Sure. So I think I get your gist. So for example, like, so we know that the line L is, let's call this problem. Let's say this is 1, 2. So we're being given that L is perpendicular to the plane. Let's say the plane is 3x minus 4y plus 2z equal to 7. And they're telling us what else, that the line goes through a certain point.
Yeah. I
Okay.
think so.
Sure. And L goes through point, I don't know, let's make it interesting. 5, 1. So make sure it doesn't actually 15 minus 4. Yeah, that's okay. 2. All right, so find the plane equation, like the previous problem, you need both a normal vector and a point. Find the line, you just need the direction vector of the line and the point. So really all we need, since we already have the point, we just need the direction. So the point it goes through is 5, 1, 2. And the direction it's going in, well, we know it's normal to this plane, and the plane, this is really beautiful that the plane equation gives you the normal vector right off the bat. So the direction of this normal line, this normal vector, is 3, -4, 2. That's it. It always kind of used to baffle me when I was student for like, I was, why is it always just like that? It's really, but it always works out. And the reason you can, I mean, if you want, we can really justify it. But really what's happening here is, right, is if you take this plane equation and you want to find any point in it, well, now I feel like I've said words that I need to show you what I'm talking about, because I would like you to believe it, even though we've talked about it before. So just to kind of remind you of why this works, if you take any point in the plane, X, Y, Z, and some given point in the plane, let's find a nice point here, 1, -1, 0. That point is definitely in the plane, right? It satisfies the equation. if you take that vector v and do the dot product of that vector with the perpendicular vector n, that dot product should equal 0 because they're perpendicular to each other. But then if we look at what n needs to be, well, we're exactly getting this vector here, x minus 1, comma, y minus minus 1, z minus 0, dotted with the normal vector, which is going to be 3, 4, 2. Sorry, 3 minus 4, 2. When we do this dot product, we exactly get 3 times x minus 1 plus negative 4 times y plus 1 plus 2 times z equal to 0. So that's why those coefficients give you the normal vector, because when you dot those coefficients with the any vector in the plane, you get the dot product equaling 0. And so you end up getting this equation. Oh, you get exactly 3x minus 3 minus 4y minus 4 plus 2z equal to 0. Or in other words, 3x minus 4y plus 2z equal to 7. This is exactly the equation we're playing.
So that's if you're given point.
Right. So I'm kind of doing something on the side here that's not really related to this. I was just pointing out that that's really why the equation of the plane just gives you the normal vector right off the bat. You can just look at the equation and be like, oh, there's a normal vector, 3, negative 4, 2. That's the reason behind it, is because you have to have this dot product equaling 0. But then if we have a point and we have a direction, we can write the equation of the line. And there's like a couple ways people like to write the equation of the line. I personally like to write it as x equals 5 plus 3t, y equals 1 minus 4t, z equals 2 plus 2t. It's always just the point plus t times the vector. So you could also write it as 5, 1, 2 plus t times 3, negative 4, 2. That's also a good way of writing it. So for a line, we just need the point and the direction. What other things should we talk about before I start doing chapter 13 things? And I mean, I just want to give you, I would love to give you the opportunity to ask questions if you have questions, because I feel like I've gotten a little bit ahead. Well, that's not true. I feel like I'm a little bit ahead, a fair amount ahead in Casala's class, a little behind in your guys' class. So try and kind of split the difference.
The difference is so large.
Right. Yeah.
Kind of confused, like in the first problem that you did, just plugged in values, but I thought you'd do the thing where it's like x minus x naught y, and then you plug into the x naught.
Find the equation of the plane.
Find the equation of the plane. So it kind of.
So yeah, that's so yes. So you can do it that way also.
Okay.
So when you're finding the equation of the plane, once you have a normal vector and a point, you can either make you can do what we did and say, you know, coefficients of your the normal vector gives you the coefficients,
Okay.
and then you can plug in your point to find the constant there, or you can totally do it this way. You can say exactly x minus, I'm going to use this point here, x minus 6 times the coefficient, I forgot the coefficient, apologies, negative 1 times x minus 6 plus 2 times y minus 2 plus the coefficient of z was 1 times z minus 1 equals 0. And then solve it, but you get the same thing. So this ends up being negative x plus 6 plus 2y minus 4 plus z minus 1 equals 0. And 6 minus 4 is 2, minus 1 is 1, and then you add to the other side, subtract the other side, it's going to be negative 1. So you get negative x plus 2y plus z equals negative 1.
Basically just doing those spread.
Right. So the different, I kind of liken this to the difference between when you're finding the equation of a line in like regular, like, you know, 2 dimensions. It's the difference between doing like y minus y1 equals m times x minus x1 versus doing y equals mx plus b and then plugging in a point and solving for b. But you're going to get the same answer either way you do it. I find this to be a little quicker, but this way is totally fine. So. Yeah. There's lots of, I mean, I think the three-dimensional stuff is kind of neat. There's lots of fun things to do. But a lot of it boils down to finding normal vectors, finding a point, finding the distance between them by either using sine or cosine. But it's kind of it's good to practice it. But I suppose we could move on to chapter 13. I know it's a bit. You guys, where is Casals at? You guys just start talking about 26. Okay, you're almost there. Yeah, we're not bad. That said, if you have questions about other things, you're welcome to bring them up. It's not like we're moving forward and we can't go back.
This isn't like starting. Yeah.
Okay.
Just like.
Okay.
We did do 13.2.
Okay. All right. But we're not too disparate here. So let's look at this. Let's say we want to do the following. We want to find vector function, is what we're going to start talking about, for the intersection of these two surfaces, x squared plus y squared equal to 4 and z equal to x squared. And just as a reminder, x squared plus y squared equal to 4 looks like a cylinder, radius 2. And z equal to x squared looks like a parabolic cylinder, right? It looks like a cylinder, it looks like a parabola that's been extended in one direction. Z equal to x squared kind of looks like this. Drawing skills here. Yeah, can I make this work? Sure. So there's your z equal to x squared. Looks something like that. It's like a parabola, but looks like a piece of paper folded into a parabola. And then we're trying to see where these kind of intersect each other. And if you kind of cross this, well, with that one, you get this kind of, well, when it crosses this, it's going to kind of hit the cylinder low on the ends and kind of high on the front and back. And let me just try and draw it here. So what's kind of going to happen is you're going to have something kind of described as like a Pringle shaped chip. Kind of do the same thing around the back. And again, my apologies for my drawing skills here. Those are not the best. Imagine you've all seen a Pringle before. You know what it looks like. That does not really look like a Pringle. Sorry. Let me, just so you can visualize it a little bit better, let's maybe actually take a look at what it looks like in GeoGebra, because I think we might as well use the tools we've got to be able to actually see things. I will also just remind everybody that you might have paid a lot of money for your textbook, and although you might not use it a whole lot, it does have really good pictures in it. So I really encourage you to look at the pictures in your textbook because they're usually pretty nice. Also for other things as well, but especially for the pictures. So if we draw these things, yeah, I don't want those. No, thank you. So let's see, we've got x squared plus y squared equal to 4. Great, cylinder. And then we also have z equal to x squared. Why would you make them the same color? I don't understand that. Not my favorite choice there. Get a different color, please. Anything else? Great, perfect, awesome. Thank you so much. Okay, great. So then we look at this thing. You can kind of see, yeah, you can kind of see where they're intersecting each other and how it's high on the sides and then low in the middle. And my words are failing me here, but you've got this shape where, yeah, you can kind of see that. You could have picked a better color maybe, but that's what we're looking at. Something that kind of looks like that. And it definitely is just a curve, right? There's this little kind of like circular curve that goes up and down between. So we're kind of looking at something. Yeah, I wish I could draw that. I want to try and draw it, but I feel like it's really not going to happen. Yeah, can I look at that one more time just to see? Yeah, there's no prayer. Yeah, my drawing skills are just. Could I do it? Maybe. No. Fail, hard fail. No, okay. Yeah, that's a no. Anyway, that's not the point. You don't have to be able to draw things to be good at math. So, although it's not a bad skill to have. The point is, we would really like to actually write an equation for this curve using not just x plus y equals 4 and z equals x squared. So what we're going to do is we're going to parameterize things. So the x and y coordinates are on the circle x squared plus y squared equal to 4. Parameterizing circles is pretty straightforward. You just kind of let x and y be sine and cosine. Doesn't really actually matter which one you pick. It is usually the default to set x equal to cosine if you have no reason not to, and y equal to sine. But really, you can interchange them just fine. And then the coefficient should be whatever the radius of the circle is. So we're going to set x equal to 2 cosine of t, and y is going to equal to sine of t. Cool. And that gives you any point on the circle, right? I mean, you can plug in values for t and get, like x could be 2 and y could be 0, or x could be 0 and y could be 2, or all sorts of other things. Right, there's your circle, radius 2. And here's where t equals 0, here's t equals pi over 2, here's t equals pi, et cetera, et cetera, et cetera. And then, well, now that we have what x and y are equal to, and we know that z is equal to x squared, we can just say, great, z equals x squared. That's going to equal 2 cosine of t quantity squared, which is just 4 cosine squared of t. So then we can describe the vector valued function as just the x, y, and z coordinates and in terms of your parameter t. So we can say that r of t, the position vector of this curve, is going to be given by 2 cosine of t, comma 2 sine of t, comma 4 cosine squared of t.
So R of t is called the position vector.
Correct. And it describes, typically we think of this as the position of a particle in space at time t. Position of a particle at time t. We don't typically specify, but here you could note that t only needs to go between 0 and 2 pi to get the whole curve. So you could point out here that we only need t to go between 0 and 2 pi. Although usually that's not really talked about unless you're being asked specifically for that. Usually we just kind of like, yeah, whatever, t's doing its own thing. Right, exactly. So t could have the domain everything, but it's fairly typical to kind of use the smallest interval for t that you need to get the entire curve. But again, yeah, most of the time you wouldn't even say anything. You just say, yeah, there's your curve, and t can do whatever. So then if you wanted to, right, you could find points on the curve by picking values for t. So for example, right, if t is equal to 0, you're going to get the point 2, 0, 4. And if t is equal to pi over 2, picking just easy values, right, you're going to get the point 0, 2, 0, and so on and so on. Cool. So there's a number of things we can do for each of these vector functions. Each vector function, we can determine the following. A, where the particle begins, meaning its initial point at time equals 0. And then its direction of travel Sometimes this makes more sense than others, but specifically for circular things, we typically talk about it being either clockwise or counterclockwise. We can also ask, is the speed of the particle constant? And then we also like to ask things like if the acceleration is perpendicular to the velocity. It kind of seems weird to think about, but if you're traveling in a circle, right, typically we think about the velocity being kind of tangential to the path you're taking, and the acceleration is typically somewhat inward because of, like, I think about a thing a kid would do, like taking a piece of rope or chain or something and just kind of spinning it around and think about the thing on the end of it, what it's doing, but it's still kind of, it's accelerating inward because it's not just flying out into space. Again, my physics knowledge is not super great. Definitely talk to Duff. Duff knows all the physics things. He's not here today though, right? Virtual something. Yeah, I don't know what Duff is up to today, but you know Duff, he does physics. Talk to him. Anyway, so we can find these things, and to find, say, where the particle begins, well, that's just going to be r of 0. And we're still using the same, actually, let's actually use a slightly different example just for the sake of niceness. So before we get here, sorry, apologies. Let's say our new position vector is just going to be just the circle. We're not worrying about the z coordinate. We're just working in 2 dimensions because James can draw that. And let's actually make it a circle of radius 1. Let's say it's cosine of 2t in the I direction, plus sine of 2t t in the j direction. As I will frequently remind you, there are lots of ways of writing vectors. This is a perfectly fine way. You could also write it using the bracket notation, cosine of 2t, sine of 2t. Also totally fine. I don't think there's any, I mean, they have their uses. Sometimes one's nicer than the other for whatever reason, but use what you like, unless your teacher specifically demand you do it one way or the other. Usually people don't really care. So where does this particle begin? Well, in fact, what is this describing? So we want to get very comfortable with the fact that when you see cosine plus sine, or sine plus cosine, or cosine minus sine, or sine minus cosine, I should really say cosine times I plus sine times j, or cosine plus times I minus sine times j. Anything like that is almost always going to be a circle. We know this is a circle because this is our x coordinate. This is our y coordinate. And if we square those and add them together, x squared plus y squared is equal to cosine of 2t squared plus sine of 2t squared, and that's equal to 1. Trig identity. And if your equation is x squared plus y squared is equal to 1, that is definitely a circle of radius 1. Cool. So I'm going to want to draw this on another page. But to kind of answer the first question, where are we starting? Where does our particle start? Well, r of 0 is cosine of 0 times I plus sine of 0 times j, which is going to be the point 1i plus 0j, or just I. So we're starting at the point 1, 0. Great, let's draw some pictures. Pretty good circle. And draw a circle, all right. So here's where we're starting at time equals 0. And then the next question is, what's our direction of travel? And to me, the easiest way to find the direction of travel is literally just to plug in a later time value and see where you're at. Now, the problem is if you go too big, you won't know. For example, if I plugged in, say, like t equal to I over 2, that's actually not going to help me because r of pi over 2. Right, exactly. It's going to give me cosine of 2 times pi over 2 I plus sine of 2 times pi over 2 j. And cosine of pi is -1 and sine of pi is positive 0. So you get -1, 0. So great. I know that at time equal to pi, I'm over here, but I don't know which way I got there, right? Did I go up and over or down and under like that? So I need to pick a smaller value for t to actually know which direction I traveled. So I'm going to pick t equal to pi over 4. And then r of pi over 4 is going to be cosine of 2 times pi over 4 plus 2 times pi over 4, which is pi over 2, plus sine of 2 times pi over 4, pi over 2, j. And cosine of pi over 2 is 0. Sine of pi over 2 is 1. So halfway between time equal to pi over 4, we end up at the top of the circle. So we definitely are going this way. Or in other words, we are going counterclockwise. There are lots of ways to parameterize the circle, so you can go kind of whichever direction you want. It's typical to go counterclockwise though. What about the speed? So is the speed constant? Well, the better question is, how do you calculate the speed of a vector valued function? Particle moving with position RT. Exactly. Speed is the magnitude of velocity. Where velocity also is a vector value function. So v of t is just going to be the derivative of r of t. Is going to be, I should probably write down my function again. I know it's over there, but just so we all have it on the same page here. R of t, one more time, was cosine of 2ti plus sine of 2tj. Keep wanting to write j there instead of t. Okay, so the magnitude, well, let's find first of all just the velocity vector. So we take the derivative. Derivative of cosine of 2t is negative sine of 2t times 2. Still in the I direction, and the sine of 2t is going to be plus cosine of 2t times 2j. So there is our velocity vector. Write it again, just because I feel like I wrote it kind of gross. It's -2 sine of 2t, comma, +2 cosine of 2t. And the magnitude of that, well, we know how to find the magnitude of a vector. You're just taking the square root of the sum of the squares of the components. So the magnitude of the velocity here is going to be the square root of -2 sine of 2t squared plus 2 cosine of 2t squared. And that's going to end up being exactly the square root of 4 sine squared of 2t plus 4 cosine squared of 2t, which is just the square root of 4 times 1, which is just the square root of 4, which is 2. So the answer is yes. The velocity has, or the particle has a constant speed. It's interesting to talk about kind of how the velocity is working here. We want to talk about velocity for a second. We can say that v of 0, if we just plug in 0 to our velocity vector, we're going to get -2 times sine of 0, which is 0, and 2 times cosine of 0, which is 2. So at time equals 0, at this initial spot here, here is our velocity vector. It's going straight up. I didn't draw it as big as it probably should be, since this is a circle of radius 1. That velocity vector should probably look like twice as big as the radius of the circle, but I'll have something true. And then if we go over to, like, say at time equals pi over 4, v of pi over 4 is going to equal, well, let's see, if I plug in pi over 4 here, I get -2 times sine of pi over 2, which is going to be -2 times 1, and then 2 times cosine of pi over 2, which is going to be 0. So at this point right here, pi over 4, the velocity vector is going straight to the left. So maybe not surprising, I don't know, but right, the particles traveling around the circle like this, and at any particular moment, its velocity vector is just tangential to the direction of travel. So I'm right here, I'm moving that way, my velocity is that way at that moment. And we can do that anywhere, right? Right here, the velocity vector would look like that. Over here, the velocity vector would look like that. And they should all be the same length because the speed is constant. I haven't drawn them particularly the same length or not, but that they should be all the same length because the magnitude of the velocity is just a constant of 2.
If that's the case, then the velocity dotted is the position of 0 at any given point.
Believe so. That seems correct. We could certainly check it out. I'm curious. So let's say, what is the position vector dotted with the velocity vector? Well, let's see. Our position vector was, cosine of 2t, sine of 2t. And our velocity vector was -2 sine of 2t, comma 2 cosine of 2t. Yeah, it certainly looks like they're going to dot product out to 0. So we're going to get -2 sine times cosine, so -2 sine of 2t, cosine of 2t, plus sine times 2 cosine, so 2 sine of 2t times cosine of 2t. And yep, those certainly do end up equaling 0. Not always the case, but it certainly is in this case that the dot product of the position and the velocity vector is 0. It's not, well, I don't know, actually. Again, the physics is not great with me here. It might be true that the position and the velocity vector are always perpendicular to each other, but I feel like it's probably not always true. Let's ask the last question. Is the acceleration perpendicular to velocity? And the answer is going to be yes, but let's go ahead and see. So just like here, velocity is -2 sine of 2t, 2 cosine of 2t. That's our velocity vector. Then our acceleration vector, just being the derivative of that, well, I get derivative of -2 sine of 2t is going to be -4 cosine of 2t. And the derivative of 2 cosine of 2t is going to be -4 sine of 2t. If we dot those together, we're going to get that times that. So we're going to get 8 times sine of 2t times cosine of 2t. Those multiplied together, we're going to get -8 times sine of 2t times cosine of 2t. Those definitely cancel each other out. We get 0. So yeah, acceleration is always perpendicular to velocity. Interesting. It means we are always accelerating inward in this particular example. So let's look at a more interesting example, but still a circle. I know the circles get to be a little bit boring, but they're worth exploring because they're easy to look at. So let's look at a slightly different example, which you would maybe think would be the same. It's going to be a little bit different. So let's say we have now this vector valued function, this position function. R of t is now cosine of t squared, sine of t squared. Still describes a circle. So still a circle. And we still have the initial position being cosine of 0, sine of 0, just 1, 0. What about the direction though? Well, for me direction, I just like to plug in a later point. So if I plug in a later time, like, I don't know, something that's easy to plug in, I'm going to think maybe like the square root of pi over 4. At a later time, then r of the square root of pi over 4 is going to give me cosine of pi over 4 comma sine of pi over 4, which is certainly ending up in quadrant 1, right? That's going to be root 2 over 2 comma root 2 over 2. So we're still thinking counterclockwise. Right, we're starting at 1, 0, and then later on we are at, I draw a circle, maybe. And later on at time equals pi over 4 right there. So we're definitely going that way. All right, what about velocity being, I should say, what about the speed being constant? Well, find out. We're going to take these, these definitely do get a little bit tedious once the functions get more complicated. First, we're going to find the velocity. So it's going to be, let's see, the derivative of cosine t squared. Oh, we have to be a little more careful here. Derivative of cosine t squared is going to be negative sine of t squared times 2t. And derivative of sine of t squared is going to be cosine of t squared times 2t. So now if I want to find the magnitude of the velocity, it's going to be the square root of that squared plus that squared. So it's going to be negative 2t sine of t squared plus 2t cosine of t squared. When I simplify that, let's see, I'm going to get, so here's what if I was trying to be efficient about this, I see I'm going to get a 4t squared here and a 4t squared here, and this will factor out. If I factor out the 4t squared, I'm left with a sine squared of t squared plus a cosine squared of t squared. And those do cancel. Or not cancel, sorry, they add to 1 trig identity. So this is really just going to be the square root of 4t squared, which is really just 2 times the absolute value of t. Square root of 4 is 2. Square root of t squared is the absolute value of t. Which makes sense, right? Because, well, first of all, t could be negative, right? It's totally fine to plug in a negative time. But the magnitude of velocity certainly shouldn't be negative, right? We're not talking about negative. Speed is not a thing that gets to be negative. Speed is always talked about in a positive way. If you're talking about negative speed, you're talking about velocity. So that's another way of justifying here why when you take the square root of t squared, you should get the absolute value of t. Definitely not constant. Right, as time goes on and on and on, this particle is really picking up speed. If you go around and around and around the circle a bunch of times, this particle is going to be really super fast. Which maybe doesn't make any sense at all, but this is the example. Questions about either of these things before we do the last part here? Okay, so are acceleration and velocity perpendicular to each other? No idea. Let's find out. Acceleration. To find the acceleration, we have to take the derivative of velocity. That's going to be, I got to use the product rule here. Okay, let's be a little bit careful. So it's the derivative of negative sine of t squared. So it's going to be negative cosine of t squared times 2t times the other 2t that's there. Plus, then it's the negative sine of t squared left alone times the derivative of 2t, which is 2. Comma, then we do for the other part here. The derivative of cosine of t squared is negative sine of t squared times 2t times 2t plus cosine of t squared times 2. It's gross. I would probably simplify this a little bit. Yeah, I would. So a of t is going to equal negative 4t squared cosine of t squared minus 2 sine of t squared, comma, and then we have a negative 4t squared sine of t squared plus 2 cosine of t squared. And just so we can see it right there. And as a reminder, our velocity vector is just negative 2t sine of t squared, comma 2t cosine of t squared. Now we're going to find the dot product. Looks terrible, but we can do it. Right, and that's something that actually is going to come up not infrequently. Is your vector valued functions are going to be kind of gross sometimes, and especially when you start taking the derivatives to get the acceleration or the velocity, they're going to get nasty. But if we dot these together, let's find out what happens. So, all right, so this dotted with that, I'm going to try and be a little bit smart with my work here. So negative 4t squared cosine t squared times negative 2t sine t squared is going to give me a positive 8t cubed cosine times sine. Then I also have this part multiplied by it. So negative 2 sine of t squared times negative 2t sine of t squared is going to give me a plus 4t sine squared of t squared. Okay, I've dotted the first components together. Now let's do the second components. So this with this is going to give me minus 4t squared times 2t is a minus, let's write down here, minus 8t cubed cosine of t squared sine of t squared. Great, that's going to cancel out. Nice. And then 2 cosine t squared times 2t cosine t squared is going to give me 4t cosine squared of t squared. And these do cancel, but the other parts don't. So we end up getting that this is equal to 4t times sine squared of t squared plus cosine squared of t squared, which ends up just being 4t times 1. So acceleration and velocity are not perpendicular to each other. And I believe, although you should probably check it out for yourself, you do get acceleration and velocity being perpendicular to each other when speed is constant. When speed is not constant, you don't get that. All right, that is enough for today.